Okay, let's do one more example. So our task, we want to calculate the electric field at point A. So let's just draw the scenario. So I'm going to put a charge here and a charge here. So I'm going to call this one Q1. So Q1 is going to be given a charge of negative 50 microcoulombs. We're going to have Q2, and that's going to be a value of positive 50 microcoulombs. And these two charges are a distance of 52.0 centimeters. And up here is some point A. I'm going to call this A. And that is a distance of 30.0 centimeters. And this is a distance of 60.0 centimeters. And it comes out to be a 30-degree triangle. So we're asking what is going to happen at A. So before we even start, let's make a little prediction of what's going to happen. So we have a positive charge. So I'm just going to redraw it to the right over here. If we have a positive charge and if we have a negative charge, what do our electric field lines look like? We know that electric field lines go from positive to negative. So I'm going to draw an arrow from positive to negative, like so. I'm just going to draw out a bunch of field lines. So this is approximately what it's going to look like. And the question's asking what is going to happen at some point up here. So what's this this point above the 0.5 microcoulomb charge? So you see that the electric field, we follow that red line. So at that specific point, the electric field is the tangent. So we're trying to figure out what is the electric field at that point. So that is what we are expecting. So what we can do to solve for this one. So if you look at our original diagram again, we know that a positive charge will result in an electric field away from it. So I'm going to draw an arrow away from the positive charge. So I'm going to call that, because that's Q2, I'm going to call that E2. However, we know electric field lines point towards a negative charge. So I'm going to draw an arrow like so. I'm going to call that E1. And we see that when we vectorially add them together, it'll end up to look something like that resultant vector E that we drew on the right. And the reason I drew E1 to be smaller than E2 is because the magnitudes are the same, but it's further away. So we know the strength of the electric field is going to be smaller. So let's go ahead and solve for E1 and E2. So E1 is equal to KQ1 over R1 squared. So 9 times 10 to the 9 newtons meters squared per coulomb squared. The charge is 50 microcoulombs, and the distance is 60, so 0.60 meters away. So we plug that all in, we end up with the value of 1.25 times 10 to the 6. Yeah, 1.25 times 10 to the 6 newtons per coulomb. And the angle that's acting at, if I were to do a little geometry right there, it's 30 degrees south of east. That's assuming we're saying north is up, east is to the right, south and west, like so. So it's acting 30 degrees south of east. If I now solve for E2, and this value, it's the same top, so 9 times 10 to 9 is 50 times 10 to the negative 6, but the distance is half the distance. So I could just use proportional reasoning to solve for that as well. It's just going to be, the force is going to be 4 times strong because E is proportional to 1 over R squared. So if we replace that R with a 1/2 squared, you can see that's equal to 4. So our electric field is going to be 4 times greater for E2. So if I just take our 1.25 times 10 to the 6 and times that by 4, we get 5.0 times 10 to the 6 newtons per coulomb, and that is in the north direction. Now we just need to vectorially add them together. Now, there's different ways. So last time we did the previous one we did a picture one, we can also do a table. But basically we have E2 is up. It only has a y component, but E1 has both an x and a y component. So there's E1 and has an E1 x value and an E1 y value. So what is E1 x equal to? That is just equal to 1.25 times 10 to the 6 newtons per coulomb. And we're going to multiply that by cos 30 degrees. We got 1.08 times 10 to the 6 newtons per coulomb. And there's E1y is equal to, well, that's going down, so I'm going to include that negative sign already. And it's going to be sine 30 degrees, which comes out to be negative 6.25 times 10 to the 5 newtons per coulomb. Now our resultant vector, we can see that we're going to have to subtract the y values. It's going to be E2 minus E1y. Okay, so our resultant EX is just equal to 1.08 times 10 to the 6 newtons per coulomb. But EY, on the other hand, we can see it's going to be upwards. So E2 is 5.0 times 10 to the 6 newtons per coulomb, but that E1y is trying to pull it back down, so it's minus 6.25 times 10 to the 5 newtons per coulomb. We end up with 4.4 times 10 to the 6 newtons per coulomb. So those are our two values for our resultant vector. Now we just vectorially combine them together. So what we can see from that, let's erase this picture on the left. Overall, we know our vector E looks something like the following. The x component of E we found to be 1.08 times 10 to the 6 newtons per coulomb. And the y component we found to be 4.4 times 10 to the 6 newtons per coulomb. Now we need to find that angle as well. So we go a squared plus b squared equals c squared. So I'll go 4.4 times 10 to the 6 squared plus 1.08 times 10 to the 6 also squared. We get a value of 4.5 times 10 to the 6 newtons per coulomb. And if we do inverse tan of 4.4 divided by 1.08, an angle 76 degrees north of east. And that is our final answer.